The title of my presentation is Near Field Communications and Sensing Technologies. My presentation including following items. First, I'm going to give research background, why we study this topic. And then I'm going to explain the main challenges in this topic. And then near field beam training and near field localization. And then finally, I'm going to draw a simple conclusion. Okay, let's come to research background. So as you know, mobile communication has been developed very fast, even China. So the number of base stations is over 3.5 million. So this has been deployed. It's a huge number. Well, how about the future 6G? Well, multiple speakers have already predicted applications of future 6G, what the future 6G is. Well, the common understanding is that the future 6G network will realize the deep integration of real physical world and virtual digital world, and build a new world of intelligent connections. So you can see that a few speakers talked about AI, integration of AI and communication. So it's really intelligent connections. Well, the typical application of 6G include reality expansion or augmented reality, intelligent interaction, well, holographic communication, and digital twins. Well, in order to support these applications, well, future 6G networks must achieve an order of magnitude improvement in key specifications. So, for example, spectrum efficiency must be increased from around 100 bps per hertz to 1 kilo bps per hertz. So about the peak data rate, well, it should be increased from about 20 gigabits per second to 1 terabits per second. So this is a huge step. And about latency, of course, it's one of very important specification or measure. About air interface latency should be increased from 2 milliseconds to 500 microseconds. This also should be reduced. So this is a big step as well. So how to satisfy these specifications? So we need to develop a lot of advanced technologies for future 6G. One of them is the ultra-large scale antenna arrays. Well, this include ultra massive MIMO, a very large number of antenna elements will be deployed in the base station, thousands of them. Yeah, second one is a cell-free massive MIMO. Well, the base station antennas must be deployed, distributed in the whole cell, maybe 100 of them or 1,000 of them as remote nodes. And so next one, terahertz array, because of high frequency use, millimeter wave or terahertz, wavelength is very small. So a large number of antenna elements will be deployed. And finally, extremely large reconfigurable intelligent service will be used, to increase the coverage to deploy the reads close to the end users. Well, this ultra-large scale antenna array provides some very important advantages. Well, although, the high frequency millimeter wave or terahertz has a large penetration loss, but really deploy more antenna arrays to form very narrow beams to achieve high beam gains. So, this is like a compensation. And regarding width, ultra-large scale width can be used to increase coverage, in case direct line is blocked. And then we can form virtual line of sight between base station and the user. Well, there are a lot of challenges. About channel model, this is one of the big problems. Well, electromagnetic propagation includes far field and near field. The existing researches in mobile communication assume far field. When the frequency is low, for example, below 6 gigahertz, and the number of frequency is not large, the near field is very small, the range, maybe a few meters. So from base station. So in this very small range, users are very likely not in this small range. So therefore, near field has been ignored in mobile communication. However, as the frequency increases, from low frequency to millimeter wave to terahertz, the number of antenna elements increases significantly. Well, the rayleigh distance, which distinguish near field and far field, will be large. So, for example, when the size of the antenna array, the angle direction D is 0.5 meter and frequency is 60 gigahertz, that's millimeter wave, the rayleigh distance can be 100 meters. So if the antenna at the plane is larger, for example, 1 meter, frequency 60 gigahertz, the rayleigh distance can be as large as 400 meters. This is large range. So in this large range, most of users can be. So therefore, near field propagation is important. Well, in this near field propagation, we need to use more accurate channel model. So that is a spherical wave instead of a plane wave for far field. So therefore, ultra-large massive MIMO does not only introduce large antenna elements, but also the significant change in the channel model. So we have to use accurate channel model for communication and sensing or localization for future 6G. Now I would like to provide some comparison of the channel model between far field and near field. Well, the left-hand side is far field plane wave, and the right-hand side is near field spherical wave. So you can see, first of all, the angle of arrival in the far field can be approximately the same, equal. That means the angle of arrival is the same for all antenna elements in the far field, so in the plane wave. But however, the angle of arrival in the near field is different. It's not equal for each antenna element. So you see the angle theta on the other side can be different from antenna element to antenna element. So this is one of the big difference. Well, regarding phase response on the nth antenna element, so you see the two equations. The left-hand side shows the phase response for the plane wave. So this equation is relatively simple. So you can see it's minus 2 pi divided by wavelength times the antenna index n times the antenna separation d, and then cosine theta. Again, theta is angle of arrival. But in the right-hand side, you see the phase angle on the nth antenna is more complicated. So it's minus 2 pi divided by wavelength, and then multiplied by the complicated term square root R square. R is the distance between the central antenna element to the end user, and then plus the antenna index square multiplied by the square of the distance between two antenna elements, and the minus 2Rn times d times cosine theta and the minus r. It's more complicated. From these two equations, we can draw a big difference between the far field and near field. First of all, the phase response in the far field is linear relative to the antenna index n. You see, it's really linear function of n. But however, on the right-hand side, you see this response is non-linear. You see, it's square root, and then and then n is n squared there is really non-linear. And the third feature is that the phase response in the far field is mainly a function of the arrival angle, theta, is one-dimensional. But however, on the right-hand side, in the near field, you see the phase response is not only function of angle of arrival, but also function of the distance, r. So this phase response in the near field is two-dimensional, not one-dimensional. So this is a big difference in the channel model between near field and far field. Well, the second technical challenge in the ultra-massive MIMO is beam training. So as you know, for the massive MIMO, we have to form very narrow beam to the end users, so we have to do beam training. Well, in the far field, basically we use discrete Fourier transform codebook. This has been widely used. Well, this DFT codebook has some features. First of all, code words are orthogonal to each other. And regarding the sampling on the angle, the number of code words is small because it's one-dimensional. Well, the number of code words is equal to the number of antenna elements, so it's relatively simple. Well, about the beam training, well, this beam training, again, is one-dimensional. In the far field, yield is relatively far away from the base station. So we may consider the NU slow mobility, and the channel is more stable. Well, about the beam training, we may use exhaustive search scheme. So in the uplink, we send pilot, and the base station, test the performance of each code in order, and then to find out the best code word. So is this suitable for near field? Well, in the near field, first of all, this DFT code books are not suitable for this spherical wave channel. Well, in the near field, we have to consider not only angle of arrival, but also distance. So this is really two-dimensional. So this is a big step from one-dimensional to two-dimensional. And therefore, the number of code words has been increased significantly. One-dimensional is simple, but two-dimensional is a matrix, as you know. So number of code words is huge, so it has been increased significantly. Therefore, it's very challenging for the near field beam training. So if we still use exhaustive search, it's very complicated. The pilot overhead will be very large. So the key question in the beam training, that's two-dimensional beam training, is how to reduce overhead. Well, now I would like to present about this beam training. First of all, far field beam training. Well, in the far field beam training here, I present, the method. First of all, we may use exhaustive search. This is very complicated, but really provide optimal beam training. So this is really optimal. But on the other hand, we may use a hierarchical search scheme. That means, when number of beams is very large, we may reduce the complexity by using this hierarchy. First of all, we consider wide beam, and then within the wide beam, we search a narrow beam. So is this possible to use the hierarchy scheme for near-field beam training? Yeah, it's possible, but we have to consider the feature of the near field. It's two-dimensional. So if we still use this traditional hierarchy scheme for this two-dimensional beam training, it's still complicated. So in this near-field beam training, we propose again AI application. We propose a beam training scheme basically based on a deep convolutional neural network. So we consider wide beam first for this far field, and then because this wide beam considers some information of the near field beam. So we test field wide beam and then training, and then search the best near field cohorts. So this block diagram shows the scheme. This basically we use dual neural network. So from the same input, this pilot input, we build separate neural networks. That's dual neural networks architecture. One for estimation of angle, another one for estimation of distance. And then we find out the optimal angle and then optimal distance, and then get the beam training. So, and then I just want to give a presentation because of time limit. This figure shows the achievable rate as a function of transmit signal to noise ratio. The block curve shows the performance of the executive search, and the lower curve shows the performance of the dual convolutional neural network. So it can be seen that as the signal to noise ratio increases, you see the gap between the optimal one and the neural network is very small. So from this figure, we can conclude that achievable rate can be very close to that of the executive method. Regarding the pilot overhead, the right-hand side, the table shows the pilot overhead, for executive search, hierarchical search, and the proposed scheme. It can be seen that the pilot usage for the proposed scheme is only 5% of that of the executive search. So we can achieve 95% reduction in the required pilot overhead. And next, I would like to spend just a few minutes to present the near field localization. Well, sensing is also important. So, currently the sensing research work consider, again, far field model. So even the near field model has been used. Most of the work mainly analyze or provide Cramer-Rao low-bound performance. Well, in this work, we consider the right-hand side, the scenario, the linear antenna array in the access point, and then two access to end users, and then the signal is blocked by the wall, and then we deploy RIS, large, massive scale RIS. So the RIS is massive. Number of reflecting element is large. So, and this figure shows roughly the performance, the accuracy, or the position error of the localization. So the blue curve shows the performance of the far field model, and then the red one shows the error of the near field model. So the horizontal axis number of RIS elements. So it can be seen that the performance or the error of localization for the near field decreases as the number of RIS element increases. Why, the error increases for the far field? Because it does not use accurate channel model. And then finally, I would like to draw a simple conclusion. In the 6G, as earlier speakers predicted, a lot of application, a lot of advanced technology must be developed. Well, one of them is ultra-large massive MIMO and the RIS. Well, but this causes a near-field effect. Well, this near-field channel is of spherical wave, not a plane wave. The second one is beam training in the near-field environment is two-dimensional, not one-dimensional. It's not only function of angle arrival, but also function of distance. So the second one, the positioning error in near-field environment is much smaller because of active channel model. Thank you very much.